Thank you, everybody. This is the third session in the Services and Offerings track. Thank you so much for coming. I'm excited that Chad Schmutzer and Chris Malik are going to present Amazon ECS. Chad is exceptionally deep in Linux and Docker and similar technologies. He's been a solutions architect for Amazon Web Services for a few years now. And Chad has been anchoring our solutions architecture for education in Southern California. I'm also very excited that Chris Malik is here to present. Chris is Associate Director for Academic Development at Caltech, and he manages academic development services in the Information Management Systems and Services Department. Thank you so much for coming, Chris. I really appreciate it. With that, I'll hand it over to Chad. Thank you so much, everybody.
Thank you, Larry. So hi, everyone. Can you hear me okay? My mic on? All right. So thanks for coming today. Again, my name is Chad Schmutzer. I'm a solutions architect with Amazon Web Services based out of Southern California. My primary customer base is our education customers and education technology customers. So in this session today, I'm going to talk about Amazon EC2 Container Service with Docker. Then I'll turn it over to Chris, and he'll talk about the campus migration of their intranet portal to containers using ECS. Chris and I worked together for many years at Caltech, so I'm really thrilled to be here today presenting with him. All right, so quick show of hands, who in this room has heard of containers or Docker? Okay, excellent, excellent. And who is using Docker or containers? Okay, good amount. Okay, so that's fantastic. So I'm going to quickly cover why you should consider using containers, give you a very high-level overview of Docker itself, and then I'll dive a bit more into the EC2 container service itself. And hopefully by the end of the session, you'll be as excited about containers and Docker as I am. All right, so why containers? Let's think about why you should consider moving to containers in your environment. All right, so here's a very common scenario that I imagine most of you in this room have encountered, right? So maybe you have a different group of development teams that are developing on different application stacks. Maybe some of them use Python, maybe some use Ruby, others use Java. Or maybe your dev tested environment runs on a different hardware platform than your production environment because of budgetary concerns or reasons or legacy reasons. Or maybe your developers like to develop on their Mac laptops using bleeding edge libraries, but the production environment is a more conservative Linux environment with a different version of the web framework installed. So does that sound familiar to any of you? Hopefully. All right, so the solution to this, I would like to tell you, is that containers can solve this problem. So containers are essentially a unit of software delivery, right? With the benefit of being extremely portable, very lightweight and consistent. They can be deployed and run in most current environments, and you can deploy and run anything you want inside the container itself. All right, so quick difference between virtual machines and containers, right? So hypervisor virtualization usually means running independent virtual machines on an intermediate abstraction layer, either on top of an OS or directly on the hardware. Containers are different in that they run in user space, right? So the memory dedicated to handling applications is run on top of the OS's kernel. They're generally considered lighter than hypervisor virtualization, and that means there's a lot less overhead. So the concept of containers themselves have been around for quite a while. So think chroot, FreeBSD, Jails, Solaris containers, OpenVZ, LXC, right? With Docker, containers are based on the native libcontainer library. And Docker also takes advantage of C groups and kernel namespaces to provide isolation of processes, resources, network, and file systems. Each container has its own process environment, virtual network interface, and a root file system. The file system itself is copy on write, meaning it's layered, it's very fast, and it doesn't require much disk space. Standard in, standard out, and standard error are collected, logged, and made available to you. And you can also create a sudo TTY and log in with an interactive shell on the container itself if you'd like. All right, so you might be thinking that sounds interesting, but why should I really use containers? So there's 4 key advantages and benefits to using containers, right? The first is that containers are very portable. The image itself is consistent and immutable. No matter where you run it, where you started, it's the same. That makes the dev lifecycle simpler, right? The image that works on the developer's laptop also works in production. Whether I start it today or I start it tomorrow or whether I scale it, it's going to be the same exact thing. There's no surprises. The entire application itself is self-contained, right? The image is the version, which makes deployments and scaling easier because the image itself includes all of the dependencies. And images are usually small, in the tens of megabytes of size, and that makes them very, very shareable. Containers are also very flexible, right? You can create clean, reproducible, and modular environments. So whereas in the past, multiple processes would run on the same OS, maybe you have a Ruby layer, a caching layer, a log pushing layer. Now containers make it very easy to decompose an app into smaller chunks. Things like microservices that allow you to reduce complexity and letting teams move faster while still running processes on the same underlying host. And that avoids issues like library conflicts, and it streamlines both code deployment and infrastructure management. The third advantage is that Docker images are fast, but saying that Docker images themselves start fast sells the technology short, as speed is apparent in both performance characteristics and in the application lifecycle and development benefits, right? So yes, containers do start quickly because they're really just firing up a new process on the system, but every container can be a single-threaded development stream with less interdependencies, right? So that means individual development teams can focus on their own lifecycle without worrying about conflicting with each other or with the base operating system. And there are also operation benefits, right? So for example, if the central IT group maintains the base Docker image, the developer can simply do a new Docker build. He can pull in that base image, and then he can really get back to focusing on his app and making the whole streamlining the whole process to be faster for the build and release cycle. And finally, containers are efficient, right? So you can allocate exactly the resources you want. The very specific amount of CPU, RAM, disk, network, et cetera, can all be very fine-grained and fine-tuned for your container. And since it shares the same OS, kernel, and libraries, containers effectively use less resources than running the same processes on different virtual machines. All right, so let's look at some common use cases for containers, right? So containers make it easier to build and deploy things more rapidly because the environment is the same. Building the container in dev, pushing it to test, releasing it to prod. This can also be very useful for customers running in hybrid environments where you need to be sure that you're deploying the same exact environment no matter where you're ultimately deploying to. Containers make it easier to keep consistent environments for service-oriented architectures or microservices. Also, many of these services aren't very resource intensive, so you can place them together on a shared single instance. Sometimes customers have very short-lived workflows that need entire environments set up for them, maybe a queuing system, a continuous integration system. That doesn't always map too well to the hourly per billing model method of an EC2 instance, right? So Docker can be one workaround for that, allowing them to push and pop containers onto the instance as necessary. And then you can also build isolated execution environments for testing code, maybe a playground for a Go environment or similar. Okay, so let's take a second to understand exactly what Docker is, right? So Docker is a platform designed to help automate deployment and application containers, right? So it provides tools to manage and deploy your applications with tools such as Docker build, Docker pull, Docker run, et cetera. Essentially, Docker came along and made it very easy to build, use, and to manage containers. So this is what a very common Docker environment looks like. So you have Docker running on the host environment, which is effectively the Docker daemon. The images themselves are being stored in a Docker repository, a Docker registry, such as the EC2 Container Registry Service or Docker Hub. And then the Docker client is used to build, pull, and run Docker images on that host. In this example, you can see we have multiple containers running different images with different base Linux distributions, all independent of the host operating system, which is a very powerful thing to think about. All right, so now let's talk about the EC2 Container Service and how it handles cluster management. All right, so scheduling resources on a cluster is much like scheduling a meeting, right? You need to find an open availability and perhaps a meeting room with some specific requirements, maybe number of seats, maybe a projector, et cetera, all right? The Docker CLI itself is great if you want to run a single container on your laptop. Maybe you're just going to fire off Docker run my image and your container is started and you're ready to go for that single container. But what happens when you do this, right? So scaling to hundreds of containers is a very challenging thing. Now you're suddenly managing a cluster, and cluster management is hard. You need a way to intelligently place your containers in instances that have resources, and that means you know to know the state of the cluster at all times, right? You need to know things like what instances have available resources like memory and ports available to me. How do I know if one of these containers dies? How do I hook into other resources like elastic load balancing? Can I extend whatever system I currently use, maybe my CD pipeline, my third-party schedulers into the environment? Do I need to operate another piece of software? So these are all questions and challenges that our customers had, which led us to build Amazon ECS. All right, so the resource manager in ECS is responsible for keeping track of resources like memory, CPU, storage, and their availability at any given time within the cluster itself. The scheduler is responsible for scheduling containers for task execution, right? So the scheduler contains algorithms for assigning tasks to nodes in the cluster based on the resources required to execute the task. So to properly schedule something, you need to know your constraints like your memory and your CPU. You need to find resources from your cluster that meet those constraints. You need to request that resource and then confirm that resource is actually available to you. So the scheduler is also responsible for task execution lifecycle. So to monitor that task, to check whether it's alive or dead, and should that task be rescheduled. So these are all responsibilities of the scheduler within the ECS environment. So ECS provides a simple solution to cluster management, right? We have a cluster management engine that coordinates the cluster instances, which is really just a pool of CPU, memory, storage, and networking resources. At the end of the day, the instances in an ECS cluster are just EC2 instances running our agent that are then checked into your cluster, right? So you own them, they're in your account, you can SSH into them if you'd like. ECS clusters are dynamically scalable. So for example, you can use things like the native auto-scale service within AWS. And it's possible to have a cluster of a single instance, 10, 100, or even 1,000 instances within an ECS cluster. And then you can also use ECS clusters to separate or segment particular purposes like dev test environments from production. All right, so on each EC2 instance, we have an ECS agent that communicates with the engine and processes the ECS commands and turns them effectively into Docker commands, right? So the ECS agent itself is really just another container running on the EC2 host, right? The agent itself instructs the instances to stop, start containers and to monitor the used and available resources. And the agent itself is open source and on GitHub, and we developed the agent completely in the open. So we'd love to see your pull requests and any contributions you would like to make to the ECS agent itself. That would be fantastic to hear from you on GitHub. But really what is unique about ECS is that we decouple the container scheduling from the cluster management, right? So we've opened up the ECS cluster manager through a set of API actions, and that allows you to have full access to cluster state information about the key value storage within ECS, right? And so this set of API actions forms the basis for solutions that customers can build on top of ECS, right? So if you want to integrate your own CI/CD environment or your own scheduler, those can all be integrated via the powerful API. So that API also allows you to connect different schedulers to ECS, right? And a scheduler really just provides logic around how, when, and where, and to start and stop containers within your cluster. And so the Amazon ECS architecture is designed to share the state of the cluster and allow customers to run as many varieties of schedulers as you'd like. So for example, bin packing, spread, et cetera, as needed for your own application environment. All right, so what are some of the benefits of ECS, right? So the reason we developed ECS was because customers had already been running Docker on EC2 for quite a while. Customers came to us and said it was very difficult to run these containers at scale. It really generally involved managing and installing cluster management software. So ECS itself provides the following benefits. It eliminates cluster management software. It manages the cluster state. It manages containers. It provides control and monitoring, and it can help you scale from 1 to 10 to hundreds to thousands of instances and containers on those instances. So Amazon ECS itself has 2 built-in schedulers for optimal instance placement, right? A scheduler for running long-term applications and services, and another for running short tasks and batch jobs. So as discussed before, ECS provides you a power set of APIs, right? Allows you to integrate your own custom scheduler as well as other open source schedulers that you might be interested in using with ECS. And all this allows you to have a very flexible method for doing scheduling on top of ECS. And also, ECS is also built to integrate and work with the other AWS services that you value, right? So you can set up each cluster in its own virtual private cloud. You can use security groups to control network access to your EC2 instances. You can store persistent information on EBS, and you can route traffic to containers using a load balancer with ELB. CloudTrail integration is in place to capture your API calls for security analysis, to record change tracking, and for compliance auditing, which is critical. All right, so as discussed before, ECS has a very simple set of APIs, and that allows you to be very integrate with your existing environment and to extend what you already have in your existing environment, such as maybe a Jenkins build CD/CI process, right? And the CLI is also open source and available on GitHub. So not only is the agent, but the CLI for ECS is also on GitHub. So I highly encourage you to look at those open source projects and contribute to us as you see fit. All right, so to sum everything up, ECS allows a reduction of the amount of code that you need to go from idea to implementation when building distributed systems, right? So rather than having to run Mesos or another cluster management software to manage your set of machines, you can use ECS to manage your instances and your containers directly. So the ability to run multiple tasks on a shared pool of resources can also lead to higher utilization and faster task completion. All right, so let's quickly walk through the basics of running a service with ECS. You can model your app using a file called a task definition. This really defines your containers that you want to run on ECS. All right, to create a task definition, you go to the console, you specify a Docker image you want to run, you specify CPU, memory, ports, volumes, etc. All right, you can also do all of this in JSON if you'd like, rather than having to use the GUI. So once your task definition is created, you schedule a task onto an instance with the available resources that you've asked for that task. A task is really an instantiation of a task definition. You can have a task with just one container. You can have 10 that work together on a single machine. Maybe you've got Nginx with Redis or Rails in front of it or behind it. And sometimes people ask me, what about cross-hosts? You can't do cross-host linking, right? If you need to do that, you want to use multiple tasks and link them together to talk via the network, via an ELB or something like this. The ECS also has a scheduler that's good for long-running applications. You can reference a task definition and the number of tasks that you want to run and optionally place them behind an ELB automatically via deployment. And the scheduler will then launch the number of tasks that you've requested. The scheduler will also maintain the number of tasks that you want to run and have it automatically load balance behind a load balancer if you so choose. So scaling up and down is very simple. You simply tell the scheduler how many tasks you need, and the scheduler will automatically launch more tasks or terminate tasks based on what you've asked for. Updating a service is equally easy, right? So you deploy a new version of the scheduler with launch, and the scheduler will launch tasks with the new application version. It will then drain the connections from the old containers and remove those containers, and it'll then leave the newest containers running behind your load balancer. So that's all I have. I'm going to now turn it over to Chris. So thank you very much for your time.
Hello. Good afternoon, everybody. So as Chad introduced me, my name is Chris Malik. I am the Associate Director of Academic Development at Caltech. So let me tell you a bit about Caltech. I'm a Virginia boy, and when I moved out there, we didn't really know anything about it. If we think of technical schools, we think of MIT, but on the West Coast, I assure you, we're a big deal. So we're in Pasadena. We're in beautiful Pasadena, California. It doesn't quite look like that right now because there's a giant fire in the background. We're a top-tier university. We've been #1 in the Times Higher Education ranking for the last 5 years in a row, and we're in the top 10 of every other major ranking. Now, I'm not telling you this to brag. I'm telling you this because this is the kind of people that I work with. These are world-class researchers and students, and they have very high expectations for their IT infrastructure. On the other hand, we're small. We have only 6,400 people total. That's 1,000 undergrads, 1,200 graduate students, 300 faculty, and 3,900 staff. That's a 3-to-1 undergrad to faculty ratio. It's the lowest in the country. We also founded JPL in the 30s, and it's just up the road from Caltech. We continue to manage that for NASA. So what do? I run a group called Academic Development Services. We're part of IMSS, Information Management Systems and Services. That's our central IT org. We're small enough so that we're it. We have a few free agents out in campus, but really we do everything. My group is pretty lean. I actually have 7 people. We just hired somebody last week. But we're very experienced. We have 35 years of systems administration experience between us and about 50 years of collective development experience. You can extrapolate how old we are, all are from that. We run a lot of services on campus, about 130 websites. That's about half the websites on campus. And we also run a lot of the web applications and some big things. We run the main campus website and the thing I'm going to talk to you about today, the campus intranet portal. My main job in our group is to help people solve their problems with custom software development or with cloud services. Caltech is very pro-cloud. When I first got to Caltech 21 years ago, I was interested to hear visiting faculty come to us and say, you do such great research and you have such great instruction here, but why does your IT infrastructure suck so bad? And the reason is that while we have big needs, we have a small budget and not a lot of people to do it. Well, the cloud has really changed all that and has put us from a university where people wonder how we get along day to day to a university that people are looking to for new ideas. Our upper management has seen that, and we have a plan now to move all of our on-premise services to the cloud within 3 years. We've actually been in production in AWS since 2010 when we put our main campus website out there. We were one of the first universities to do that. Now we have many production workloads. Now I want to talk to you a little bit about the strategy of how we got to where we are today. I focused on the easy things to do first, right? So things that did not have a lot of dependencies on other services, that nothing depended on, that especially that had no data that could be compromised. We chose those first because, as you all know, the cloud has a steep learning curve, so we wanted to get our chops. And why did we choose the cloud? My director and I, from the beginning, knew that if we were going to succeed, we had to focus on the thing that we do that adds value, and that's write software that no one else can write, because we either have the domain knowledge or we have access to the right resources. Anything else we needed to outsource. So as soon as we saw outsource to someone who knew how to do things better, and Amazon just knows how to do a lot of things better than us, and we were happy to work with them. And we got a lot of things like, geographic redundancy with availability zones. We use their APIs heavily, so forth. So this is a key part of our strategy. So now I talked about our previous strategy, which was get the low-hanging fruit. Well, all the low-hanging fruit is gone. So now we're into the hard parts. And one of the hardest part is to move is access.caltech. That's our campus intranet portal. This is a large distributed system that we have hosted on-prem. It's about 50 or 60 hosts. It's fronted by an authenticating proxy server that, based on who you are, restricts what you can get to behind it based on permission roles in our database. About 90 of our key apps are sitting behind behind access.caltech. And that's most of the academic and administrative apps that people use day to day. There's really two parts to this. There's the core system, which is what my team maintains, the proxy server and its supporting applications. And then there's all the proxied apps. Here's what it looks like. So this is the login page. This allows people with a single set of credentials to get access to almost all the things that they need to do for their work during the day. And when they log in, they see a list of applications that they personally are authorized to use. Now, this is what it looks like for me. Someone else logged in would look completely different. Security is very important for this, and we focus heavily on access controls. Now, some of the key requirements I want to cover, when we're thinking about moving these to the cloud, all these things have to be covered. It needs to be highly available. Like I said, access.caltech is in our day-to-day work morning to night. So when it's down, work at Caltech stops. It has to be up all the time. Now, interestingly, it has to be performing at variable loads. People do use it, but they don't use it that heavily during the day, except for 3 times a year that we call the 10 minutes of terror. That's the 3 registrations. The student systems are behind Access Caltech, and at 8 a.m. on the start of each term, they go in and register for their classes, and we can scale it. We can hit up to 800 hits a second during those times. So scalability and performance are very important. Like I said in my previous strategy, we chose public data. This is not public data. These are our financial data, people's personal data, FERPA, HIPAA, you name it. We've got it behind here. So security is going to be extremely important. Certain core components of Access Caltech should stay up during a disaster. If we create our part of Caltech, we want people to be able to update their emergency contact info, and so Access Caltech should stay up. Now my needs are the last 2. We have, since it's so key to our business processes at Caltech, we have a lot of change requests that come into the core. So I need to be able to deploy software easily and continuously, essentially. We also have 90, like I said, we have 90 apps behind Access Caltech. Well, there's a lot of developers supporting those apps. They all need dev, test, and QA environments. There's a lot of them. So I need to be able to build those in the cloud. This is a little overview of what the architecture is. You can see right now the user goes through our on-prem HA proxy to get the load balanced pair of proxy servers. There's another set of servers that runs the apps that maintain the proxy server, and a lot of the authorization data is stored in LDAP. Then everything else is proxied through the proxy server to different services in our on-prem data center. I've broken it into 2 phases, or end phases really. Phase 1, we want to move the core stuff out. So that's this stuff. So we're going to rebuild the core part of Access Caltech. And I say we're going to. I've built it all out. It's not production yet. We're hoping to go production in a few months. It's in testing right now. So we have a VPC at an AWS. We have a continuous deployment system based on Jenkins, Docker, and Console, which is a service discovery service. We can build dev and test environments in other VPCs. And we're going to go through a VPN tunnel to get back to campus. Now, different people do this differently. I know you can use Amazon Direct Connect, but Caltech being on internet too, we have a very fast connection to our local Amazon endpoints. So we use a VPN tunnel. And later we'll pick off individual apps and move them to the cloud. This is what we've got now. I've broken things into 2 VPCs. The VPC on the left is where all of my software lives, and the VPC on the right is where the LDAP servers live. Now they're in their own VPC because they're going to be shared with a lot of other services. We didn't want other services coming into the crown jewels here. Now the real thing I want you to notice about this is the yellow things are all Amazon services, and really the key to it is the 2 sets of green boxes, proxy and core. So they're sitting in their own subnets for protection so that we can authorize them back through the VPN to get to the proxied apps. Those are ECS clusters, all right? Those are auto-scaling ECS clusters. So why did I choose to go to Docker? Well, let me tell you, I've been doing this for a long time, and my big problem has been deployment. Right, so we spend a long time writing our software, but when it comes to deployment, we always seem to fall on the floor. So I've had about 4 or 5 different deployment mechanisms I've come up with, and we're stuck in a vicious cycle. And it all comes down to one problem. I'm doing too much on live systems during deployment, right? And I like to say this is about the raw versus the cooked. So currently, we have our software, and we have a long checklist of things that we hand to the systems administrators to do to deploy things. And half the time it goes wrong, either because we left some steps out, or because prod was not quite the same as test, or because because something didn't quite work. Maybe a service wasn't available when we were deploying. So what happens is that we'll fail to deploy. It will be pushed back 2 weeks to another maintenance window, and then the deploy gets bigger because now more changes have accumulated, and now the risk is higher, and we have this vicious cycle. I need to change this. Docker does change this. Why? Because my main problem is, again, I'm doing too much. Docker allows me to bake in much more of, into my pre-build. So when I make a Docker image, I'm packaging up the OS, all the dependencies, and my software. That's a lot of what we were doing during deployment. And you're going to treat that as a software artifact that's versionable. So the second thing is, I saw some people nodding their heads when I said test wasn't exactly the same as prod. Well, now I can't guarantee it because there's still some environmental and architectural differences, but you're a lot closer. You're deploying, it's very much like anyone who's doing AMI-based deployments. It's very much like that. I know what I'm getting when I roll it out. And the other thing that has always troubled me in my tenure as a director and a manager is that I have a small team. I have to be able to hand off software from developer to developer easily. With something like access.caltech, which has so many moving parts, to get that set up on someone's desktop, that's about 10 different services that have to be set up. You're not doing that. They're going to spend 3 weeks setting that up. With Docker, it's 2 minutes. You just pull the containers down, spin them up, link them, and you've got a completely working development environment. I'm really interested in continuous deployment. Does anyone know what that means? Is anyone familiar with that term? Yeah, the key problem with deployment is that since you don't do it very often, the environment is likely to drift and you forgot what you did last time, so you never get to practice. So how do we fix that? We just do it a lot. That way you have to automate it if you're going to do it a lot, and you're going to practice it all the time and shake the bugs out. So that's what I'm very interested in. We're going to use Docker builds to run our tests. We build our containers, run the tests in the container so that you always have your test environment set up right, and then push to a test environment automatically where people can vet things. And then once we get the blessing, it automatically gets pushed to prod, all based on Jenkins. So why ECS? I can't say this enough. This is sort of what Chad was referring to earlier. If you've ever looked at any of the other Docker orchestration or Docker clustering solutions, they're very intimidating to set up. I've looked at, before we started using ECS, we strongly considered Docker Swarm. But you really need a dedicated set of systems administrators to maintain this, to have high availability in your swarm masters, and you're going to have to replicate this for dev, test, and prod, and for different application stacks. Who wants to do that? I just want to write code. And even when you're done, you're not at cloud scale. You're just at whatever scale you could afford, right? So ECS is implicitly at cloud scale, and as Chad was saying, it integrates beautifully with a lot of the key AWS services, like elastic load balancing is right in there, CloudTrail, CloudWatch. Monitoring what's going on inside your containers is not trivial if you don't have something built for you. The API is beautiful. We do a lot of scripting for our deployments, and it was almost painless. The most painless I've done yet was binding to the AWS API for ECS deployments. And one thing before, so we're poor, right? So like I said, we have a small school. We don't have tons of money. I can't afford to get Docker hosted repository or private repository. That's too much for us. So I was, before ECS repositories came out, the ECS registry came out, I was hosting it locally, and what a pain that was. So I really appreciate that we can push all of our images out to the cloud like that. So I didn't sound like a total AWS fanboy. I had to make a slide up about things that I didn't like about ECS, but I really had to struggle. One thing, it is kind of painful to debug container launch fails. It is somewhere in the AWS console, but it's not easy to find. The second one is just not true anymore since I wrote this slide. They are up to current now. The third one is interesting, and Chad alluded to it. In Docker Swarm, there's a thing called the Swarm Overlay Network where you have a bunch of machines and they make a virtual network layer on top of your regular networking so that all of your containers can find each other easily. I think it has its own DNS server and routing built in. That's fairly nice. And also, Chad addressed my last point. When I was first looking at it, you really only had one scheduling option, and that was spread. Docker Swarm has a few other ones, bin pack, like pack your containers into one Docker machine and fill that up before you move to the next one. There are some use cases for that. You can do all that through the StarTask API and some scripting, so it's really not a big deal. So challenges. The things that I ran into, it was a kind of a steep learning curve because you have to think, normally you're used to thinking of your software as your software and the OS as the thing that supports your software. When you go to Docker, you really have to start treating the OS and the software all as a single versionable software artifact. Now, again, if you've done AMI-based builds where you never touch your instances in production, you only build a new AMI and roll that out, then you're familiar with some of these things. What that means is that your development team is going to have systems experience in order to really take advantage of Docker, right? Because now you're managing things in a Unix system. For us, this was not such a big deal, but I do have some younger staff that are not that familiar with it, and that's a challenge all on its own. Or you're going to have to work closely with systems people to make sure you're setting up your containers right and just running the Linux right? You're almost certainly going to have to remediate your code to get it into Docker. At the very least, it's going to have to be able to take environment variables as configuration, right? And I know my code didn't do that. My code read its configuration out of the file system. Also, things like logging, you're going to have to remediate your code to send the logs to a different place. If you're used to sending it to syslog, you don't have syslog in your container. You're going to have to do something else and send it to standard out or standard error. The other thing is that containers are really disposable and they're nearly anonymous. What I mean by disposable is don't think that you can write anything to the file system. These things are not going to probably live very long, and it's not easy to get into them. They're not running SSH, so you can't SSH into them. You have to think of them as little software appliances. And also that means you need to start rethinking about how you manage your software stack day to day. When you're going to do debugging, if you find that your developers, your systems administrators are going in to fix things in production, there's no fix like the fix that works in production. You can't really do that anymore because this is a version software artifact. Next time you do a scaling, it's all gone. And if you were depending on reading images or writing logs to the file system, again, you're going to have to rethink that. Monitoring it can be a little bit challenging because you're going to have to have, although CloudWatch does help you with that, you do have to get inside the container and see what the container sees. And that's all I have to say. Thank you. Yeah, if you have any questions, I'm happy to answer any questions. Anybody? All right, well, if you have any, I'm sorry, I didn't see you.
You talked about monitoring the container, so I'd be kind of wondering with them, if you're popping up a bunch of different containers doing all the same tasks, and then one falls over, is there any graceful way for the person to know that fell over and I'll start over. If you pop it up, you have your mic that doesn't work. Hello?
There you go.
If you're popping up a bunch of different containers, possibly to do the same or similar tasks, and one falls over for some reason, and this is in reference to they're difficult to monitor. What can you do about, first of all, realizing that one fell over, and hopefully restarting a new one to the state where it was when it fell over?
Yeah, so that's a really good question. So partly you're going to rely on ECS to restart your containers. What's really an interesting question is when something goes wrong with a container and it doesn't fall over. How do you know which one has the problem? That's a really interesting question. As I alluded to, but I didn't expand on, containers are nearly anonymous. They don't have a host name, so if you've ever run Docker and you go inside, you ask it what its host name is, you'll get a hex string. And it has its own network on the Docker machine, so you don't even know its IP address. Logging is going to be really, really important there. So we're exporting all logs from the container out to an elk stack with a bunch of tagging along the way. So that way I can look at my logs to see what went wrong and then trace that back through its path back to the ECS machine that container was running on and then go look at it. Does that answer anything?
It does, although the other part of the question was, if it was probably doing something when it either failed or stopped for some reason, I'd like to start a new container at that same place.
Yeah, I mean, that's going to be up to your software, right? I mean, that's sort of like software checkpointing in some sense. Anyone else?
Thank you very much.
All right,
That's really
thank you.
appreciated.